Okay, this is part one of the PTJ series, models for vibrating piano wires. And we're going to go through and read each equation. Okay, the first equation is going to be right here. This is Newton's second law, and it is F equals ma, or A is equal to F divided by m, where F is the force, m is the mass, and a is the acceleration of the mass. Equation 1 here expresses Newton's second law again, where it says that the mass times the acceleration is equal to the force because of the tension in the wire, the force because of the resistance to bending of the wire, force due to friction, and the force due to the hammer striking the wire. And here would be F, the force due to tension. Here is force due to bending, resistance of bending. Here's the force of friction. Here's the force when the hammer strikes, the force that is exchanged between the hammer and the string. And here's equation number 2, which is probably the most challenging one. This is just an expression of this equation up here after we have shrunk the element to infinitesimally small size and applied calculus. First term here on the left is the MA term, where the mass is represented by rho, the density, times S, the cross-sectional area, and then it's time and the acceleration of the vertical displacement, y, and it's read as the second partial of y with respect to t, time, is equal to these forces over here. First term is the force due to tension, and it's the product of the tension T times the second partial of y, the vertical displacement, with respect to distance, x. And there's the term resistance due to bending force, and it's 4 pi squared y, which is the measure of the resistance to bending, Young's modulus. S is the cross-sectional area again, and R is a term getting a radius of gyration, R squared, and it's all times the fourth partial of the vertical displacement, y, with respect to distance. And there's another term here, which is the friction term. It's capital R, which is a constant, times the partial of the vertical displacement y with respect to time. And then the final term is the force exchanged between the wire and the hammer, which we'll talk about in a minute. Okay, here are these individual terms. This is the mass times acceleration, ma, is equal to this rho s times the second partial of y with respect to time, t. Rho is the density, s is the cross-sectional area. The term, the second partial derivative of y with respect to t is the acceleration, a, and the variable y is the vertical displacement. This term is the force term because of the tension in the string, and it's tension T times the second partial of y with respect to x. Y is the vertical displacement, X is the distance along the string. And this tension in the string is T, and this second partial of Y with respect to X represents the curvature in the wire. Okay, the bending force is 4 times pi squared times the cross-sectional area S times Young's modulus Y times the radius of gyration squared times the fourth partial derivative of Y, the vertical displacement, with respect to X, the distance along the wire. And this fourth partial derivative of Y with respect to X is a measure of how much the wire is bent. Okay, this is the force due to friction, F sub friction. And there's R times the partial of Y with respect to T time. And this partial Y with respect to T is the speed. Calculus is a way of saying the speed. Down here, the force exchange between the string and the hammer, F sub hammer, is equal to ma also, where the m is the mass of the hammer, and the a would be the acceleration of the hammer. So the acceleration of the hammer right here is equal to the force exchanged between the hammer and the string divided by the mass of the hammer. Equation 4 says that the force exchange between the hammer and the string is equal to a proportionality constant, capital K, times the compression taken to a power P. And when you put the force term together with the acceleration, here's F equals ma down here, equation 5. The mass of the hammer times the acceleration of the hammer, which is second partial of y with respect to t, that's the vertical displacement of the wire, t is the time, is equal to proportionality constant k times z, which is the compression, minus y, which is the vertical displacement, and there's the quantity z minus y taken to a power p. And again, this second partial derivative with respect to time is the acceleration. And then there's the parameter p, and then there's compression z minus y. And here's the list of the parameters. Okay, here's the equation down here, equation 6, which says that the frequency f of the vibrating string is equal to the square root of the tension, T, divided by the linear density, mu, which has units of kilograms per meter, and it's all divided by 2 times the length of the string. It can also be written by frequency F is equal to 1 over 2 times the length. Oh, that's a mistake. Times the tension, square root of the tension divided by rho S, which is density times the cross-sectional area. This should be a capital L here. I hope I've got that in the final version. All right, here's equation 7. C, the speed of propagation for a flexible string, is equal to the square root of the tension divided by mu, the linear density of the string. Okay, equation 8, the speed of propagation v is equal to c, the speed of propagation of a flexible string times the quantity 1 plus y squared times pi squared times the frequency f squared, all divided by t, the tension, times the speed of the flexible string squared, c squared. So c is the speed of the propagation speed of the flexible string. V is the propagation speed of the string that has elasticity. Okay, equation 9. Rho sub n is the partial frequency of the nth partial, and it is equal to n times the fundamental frequency f sub 1, the first harmonic, times the square root of 1 plus b, which is the inharmonicity coefficient, times n squared. And then equation 10 says that, well, here, for example, this factor here is the square root of 1 plus b times n squared. And equation 10 is b is equal to pi cubed times y, the Young's modulus, times d, the diameter of the string or the wire, taken to the fourth power, all divided by 64, times the tension T, times the length of the wire squared. And I think that may be the last equation. It is. Okay, that's the end.